all viewers and followers, good day. I thank you for taking or viewing the videos that we have released. So for today, we are going to consider flexural stress or the derived stress. Of the general form of equation that we are going to consider is SF is equal to MC over I, where SF is the flexural stress or the bending stress. And in here is the maximum moment. And C is the perpendicular distance from the centroidal axis to the fiber concerned. I is the moment of inertia. Now, in considering the moment of inertia, we have to consider whether we are having a regular geometric figure, such as a square, a rectangle, or a circle. The value of the moment of inertia for regular geometric figure can be taken from a table. Now, for irregular shape, such as a T-section, the value of the moment of inertia must be computed. Now, before we try to compute the moment of inertia for a irregular shaped figure, let us first consider the sign of the moment. Now, that will be, the sign of the moment will be significant in considering the moment of inertia of any section. So, take if the beam concave upward, the moment is positive, meaning we have in here a force acting on the original position of the beam, say acting at the mid section, supported on both ends. So the tendency for the beam is to deflect in this manner. As we can see from the illustration, this is concave upward. So if it is concave upward, we have a positive moment. If the beam concave downward, the moment is negative, meaning we have here two forces vertically downward with a support in here. So the tendency for this beam is to deflect in this manner, which as you can see, it deflected concave downward. So the moment we have in here is a negative moment. Now, considering the moment of inertia for a regular geometric figure, such as a square. So when we have a square, that is P and H in there will be equal. So whether negative or positive moment is acting, either fiber will be subjected to compression or tension. That our moment of inertia will be equal to Bh cubed over 12. The same thing with a rectangle. The base is P, altitude is H. The same thing, the C under compression and the C under tension are equal. Our moment of inertia for a rectangle will still be Bh cubed over 12. if our cross section is a circle, the C under tension or the C under compression will still be the same. I now will be equal to pi d to the 4 all over 64. So it means to say in here that from the general form of the equation, SF is equal to MC over I. From the general form of the equation, we will be considering the flexural stress under compression, which is equal to M multiplied by C, under compression over I, or SFT, that is the flexural stress under tension, is equal to MCT over I. Now, for regular geometric figures such as a square, a rectangle, or a circle, the C under compression and the C under tension will be equal. So, if it involves a regular geometric figure, the cross section involves a regular cross section, that is the C under compression is equal to C under tension. So that if the C under compression and C under tension are equal, these two equations in here will just be the same. And they will go back to the original equation or formula. SF is equal to MC over I. Now, the significance of C under compression or C under tension will be seen if we are going to have an irregular cross section. So if we have a T section, so this T section, as we can see from the diagram, we have this one in the form of a T. So a T section is considered a composite figure because there are two rectangles involved in the built-up section. That is a T section in here. If, say, we have this dimension in here is A, and this is B, this is also B, and this is A. If we have a condition that B is equal to 3A, if we have a condition that B is equal to 3A, as we stated a while ago, for irregular shape or irregular cross section, such as a T section, the value of the moment of inertia must be computed. But before we will be able to compute the centroidal moment of inertia of a built-up section, we have to establish the centroidal axis of rotation or the centroidal axis of the composite figure. In considering the centroidal axis of the composite figure, we are going to consider that is what we call the x with a bar and the y with a bar. So meaning this is the centroidal x and this is the centroidal y. Meaning that is on that point the centroidal axis of the composite figure will pass through. So we will establish the x bar and the y bar. From the general consideration, that is we can take the x bar equal to the summation of ax. And y bar is equal to the summation of ay. So this capital letter A here is the total area of the composite figure. The x in here is the x element of each of the figure in the composite. Meaning, this x in here is the x distance from a certain reference axis to establish the centroidal x and the centroidal y. The same thing with this one, that is the total area of the composite figure, and y is the y element. That means a distance from the reference x-axis to the centroid of each of the figure involved. In this particular case, we have figure number 1 here on top and figure number 2 here below. So, the first thing that you are going to consider is you project a reference axis. In projecting a reference axis, you try to examine the figure itself. If you can establish a certain reference axis in such a way that you will be able to pass through the centroid of the element or the figure involved in the composite figure. In this case, figure number 1, whose centroid is here. And figure number 2, whose centroid is located at the middle of the rectangle here. The same thing with this one. So, there is the centroid of figure number 1 and centroid of figure number 2. So, if we will project a line along the vertical, the centroid of figure number 1 and figure number 2 will coincide with a line along the vertical. So if they coincide along a line that is along the vertical, that means to say that vertical line projected passing through the centroids of the element involved will become the centroidal axis. In that case, it is the vertical, so that is the centroidal y. Now, to be able to see it clearly, let me try to have the figure larger in here. So we have here the T section, A. So there is the centroid, and that is centroid. of the pairs is second. We project a line along the vertical, the centroid will coincide, that becomes the y axis, or that will be taken as our centroidal y. So, the x bar is measured along the vertical, that is to the location of the centroid of the composite figure. So we can see in here that the centroid of the composite figure, we can say at once that the centroid of the composite figure lies along the centroidal y. Therefore, our x bar will be equal to 0. If the centroids will coincide along a centroidal axis, centroidal x-axis, the y bar will be the one to become equal to 0. So in this case, the x bar is equal to 0 and the y bar will be located. Now, to locate the y bar, of course, we apply that formula in there. So, considering that equation or that formula, for considering the centroidal y, the centroidal y is equal now to the summation of a y. Capital letter A or small letter A indicates or means to say that we will be only considering the figure composing the composite figure. And we make this line at the bottom to be our reference x. Taking that as our reference x, we can now take the y element. Y sub 2 in here, and this is y sub 1. Y sub 1 is located at a over 2 here, from this point. Plus this b here, where we are going to consider that b is equal to 3a, therefore 3a plus half of a. So that is equal to 7 over 2 of a. That is the location of the y element of figure number 1. For the y element of figure number 2, we can now have half of 3, or 3 is equal to 3a, so that is half of 3a. So that is our y element. Our a1, our a sub 1 will now be equal to the area of the first figure. That is equal to a multiplied by b, or a multiplied by 3a. And that will be considered equal to 3a squared. For a sub 2, that is also equal to a, or a multiplied by 3a, or that is 3a squared. The total now is capital letter A, that is 6a squared, for the total area. So having the y sub 1 element, which is 7 over 2a, taken in here, y sub 2 element, that is 3 over 2 of a. So we can take the summation of AY to consider the Y bar. Y bar now is equal to A1, A1, Y1 plus A2, Y2. Substituting values, Y bar now is equal to 3A squared divided by the total area. Our Y bar is equal to the summation of AY. Y bar now is equal to A1. A1 is A1 Y1 plus A2 Y2. Y bar is equal to A1. A1. So we have here that is AX bar is equal to the summation of AX. A here is small letter A. The A in here is capital A. So AY bar is equal to the summation of AY. Taking the element now, A1, A2, Y1, Y2. So substituting values at this point in here, that will be equal to A1. A1 is 3A squared multiplied by Y1. Our Y1 is 7 over 2A plus 3A squared by 3 over 2A or over the total of 6A squared. So our Y bar now will be equal to, that is 21 over 2A cubed plus 9 over 2A cubed all over 6A squared. So that will be equal to Y bar is equal to 21 plus 9, that is 30 divided by 2, that is 15. A cubed over 6A squared. A squared cancelled out by that, so that this will be simply A. Y bar now will be equal to, that is by 3, so that is 5 over 2 of A. So that is our Y bar. Now, having the Y bar now, which is 5 over 2 of A, from this point to this point is 6 over 2A, equivalent to 6 over 2A. So, we take out 0.5 or half. So, this will be 5 over 2A. So, if we project a horizontal line passing through that point, passing through this, we will say now that this is our X sub O or centroidal X. So we have already established Decentroidal X. Having now Decentroidal X, we can now take the moment about Decentroidal X. Now, why is it that we are only going to consider Decentroidal X, moment of inertia? It is because we are talking of a beam along the horizontal. So the deflection that we are going to have will be with respect to the horizontal. So we will be concerned only with the centroidal X moment of inertia. So considering the centroidal X moment of inertia for a composite figure, centroidal X moment of inertia for a composite figure, that will be equal to the centroidal X of each figure. So Ix sub 1 plus centroidal X of figure number 2. Ix sub 2 plus AD squared of figure number 1. A1 D1 plus A2 D2 squared. That is of figure number 2. So, the centroidal moment of inertia number 1 is a rectangle. So, that is bx cubed over 12. b1 x1 cubed over 12 plus b2 x2 cubed over 12 plus A1. The area 1 is 3A squared multiplied by D1 squared, meaning that D is the distance from the centroidal X to the centroid of figure number 1. Figure number 1 is here. That is the line, and this is the centroidal X. So from this point, reference X, to this point in here is 7 over 2A. The location of the centroid from the reference X is equal to 7 over 2A minus 5 over 2A, or simply A. So that will be A, simply A, that is squared, plus 3A squared multiplied by the distance from the centroidal axis to the centroid. Referring to figure number 1. My figure number 1 is here. So that is 7 over 2A minus 6. So that's right. That is A, simply A squared. Figure number 2, that is 5 over 2a with 3 over 2a, or just the same, simply a. That is the square. Substituting values now. Substituting values, that will be the base of figure number 1. The base of figure number 1 is equivalent to 3a. And the altitude of figure number 1 is simply a over, that is 2 over 12, plus, referring to figure number 2, the base is simply a, multiplied by the altitude, which is b. So that is 3a cubed over 12, plus 3a to the 4 plus 3a to the 4, or that is equal to 3a to the 4. 3a to the 4 over 12 plus 3 cubed is 27. 27. A to the 4. A to the 4 over 12 plus 3a to the 4 plus 3a to the 4. Or that is equal to 30, this one, 30 over 12. 30 over 12 plus a to the 4 plus 3a to the 4 plus 3a to the 4. So that is now 3 by 12, 3 by 12, 36. That is 72, 102 divided by 12, a to the 4. Or that is equal to 102 divided by 12 equal 8.5 a to the 4. So that will be the centroidal x, moment of inertia. So having this centroidal x, moment of inertia, the process we have done in here will be the same process that we are going to take if we are going to take the centroidal moment of inertia. The centroidal moment of inertia here, that is, will simply be equal to this D element. This D element, referring to the centroidal y, the element will be 0. So this will become 0. The V2 element will also be equal to 0. So this AB element, considering the centroidal y, moment of inertia will be insignificant. So this will simply be equal to I y sub 1 plus I y sub 2. Well, of course, the moment of inertia with respect to y moment of inertia with respect to y sub 1 will follow the px cubed over 12 plus px cubed over 12. Now, because we are referring to the centroidal y, the base now of the figure will be decided along the y. So that will be the difference between the centroidal y, moment of inertia, and centroidal x, moment of inertia. When you are talking of the centroidal y, moment of inertia, your B in here will be along the y-axis. And your x will be the one that is perpendicular to the y-axis. Now we try to solve a problem involving flexural or bending stress, which we have already discussed the principle involved or the equations and other related factors that we are going to make use in solving problems involving flexural stress or bending stress. Now, as is stated in here, a simply supported beam, 6 feet long, made of a construction steel, where the allowable stress is equal to 50,000 psi, and it is loaded at the middle with a load of 2,000 pounds. If the cross section of the beam is a square, determine its dimension. If it is a rectangle where x is equal to 2b, or if it is a circle. Now, if it is a T-section where b is equal to 3a. So the first that we are going to consider is if the cross section is a square. The next, for letter B, if the cross section is a rectangle where x is equal to 2b. For letter C, where it is a circle. For letter D, that is a T-section with P is equal to 3A. So from the diagram we have here, we can consider that the values of the reactions, simply because this is loaded at the midsection, so therefore each reaction will be equivalent to 1,000 pounds. If we project the shear and moment diagram, so for the shear, from 0 in here, we go up by 1,000. And from this point A to B, there is no change on the load. So up to this point, before, the action of these 2,000 is still 1,000 pounds. Then the 2,000 pounds will act down to a negative 1,000 in here. And from B to G, there is no change on the load. And that becomes 0 at this shear in there. Of course, the maximum moment always occurs at 0 shear, or the moment at point B is simply equal to the area from A to B of this shear diagram, which the shear diagram here, we have it in the form of a rectangle, so that the area will simply be equal to 1,000 multiplied by 3 feet, or the maximum moment is equal to 3,000 foot-pounds. And as we can see, the maximum moment is above the reference axis. So therefore, this maximum moment is now a positive moment. So if it is a positive moment, it will concave upward. So if it concaves upward, we can see that the fiber, the upper fiber, is under compression, undergoing compression. The lower fiber is undergoing tension. For letter A, that is for square, from the equation SF is equal to MC over I. If we try to consider the fiber under compression, that is now SFC equal to MCC over I. And if we consider the fiber under tension, that will be equal to MCC over I. But because this is a regular geometric figure, the C under compression and the C under tension are equal. So if they are equal, we will just simply go back to the original form of equation for considering the square. So that will now be equal to SF is equal to MC over I. We have the flexural stress at 50,000 pounds per inch squared. The maximum moment is equal to 3,000 foot-pounds. And the C, which is C under compression and C under tension, are equal. So it is from the centroid to the outer fiber, upper fiber here, or to the lower fiber, which are equal. Therefore, that will simply be equal to the side of the square, up of the side of the square. So that if this is A and that is A, so this will be A over 2. And the moment of inertia for rectangle is equal to BH cubed over 12. So substituting our values, that is now 50,000 pounds per inch squared equal now to 3,000 foot-pounds multiplied by A over 2, all over, that is BH cubed over 12. So this will be, this cancels out, that makes it 6 in there. So that will be equal to 50,000 pounds per inch squared, equal to 3,000 foot-pounds. That is multiplied by A. All over. The base of the square is A. And the altitude of the square is A, which is now Q, all over 6. So A and A here cancels out. The 6 go up in here, 50,000 goes down in here. So that is now A cube will be equal to 6 by 3,000 foot-pound. A cube is equal to 6 multiplied by 3,000 foot-pound. All over 50,000 pounds per inch squared. So we convert this foot in here because pounds and pounds can be cancelled out. What remains is a foot in here, so that if we try to convert 1 foot to 12 inches, so the foot unit and the foot unit cancels out. What remains now is inch cube, a unit for A in here. Therefore, A will be equal to the cube root of, cancelling this out, that will be 6 by 3 by 12 all over 50. That is inch cube. Or we can have the dimension A. Dimension A now will be equal to that is 6 by 3 by 12 divided by 50. That is cube root of 4.32. Cube root of 4.32, or A now. A is equal to 1.629 inches. So we can use, that is, we check it from 1.629, that is the computed value. Computed value, that is within the range of 7/8 to 3. So the denominator of the fraction of an inch we can use is over 8. So for this, we can have the lower value will be equal to 1.625. equivalent to 1 and 5/8. 1 and 5/8 of an inch. So we simply check it in there, which even without computation, 1.629 minus 1.625, that will give us a difference of 0.004 divided by 1.629. That is multiplied by 100%. That will give us much less than 4%. So we can use the lower value. So that is now 1 and 5/8 of an inch. That is for considering or having the dimension of a cross section which is a square. Now for letter B, it is a rectangle. The cross section is a rectangle where we have a condition x is equal to 2b. Now there might be a confusion on the letters that I am using in here. Now using the X and the B letter in here, small letter X and small letter B, that is on a general consideration. Because when I say general consideration, that is small letter H is always taken as the altitude. And small letter B is always taken as the base. But the dimension say, for a square, the dimension I had is in terms of the A. So that is why I used A in here. For a rectangle, that is in the general form, of course, the cross section we have here is flat. So the centroid is at the midsection. As is stated, our maximum moment is positive. So this is under compression and this is under tension. But they are equal. CC equal to CP. So still, we go back to the general form of the equation. SF is equal to MC over I. So substituting all values. Substituting all values in here, that is SF is equal to 50,000 pounds per inch squared. Equal now to the maximum moment of 3,000 foot-pounds multiplied by C. C is X over 2, the altitude, or over the moment of inertia, which is equal to Bh cubed over 12. So this is cancelled out to make it 6, which will then go up. Then there is a relationship in here. In terms of the B, we take it in terms of the B. So that is now 50,000 pounds per inch squared. 50,000 pounds per inch squared. Equal now to 3,000 foot-pounds multiplied by, we have here an X, that is equal to 2B, multiplied by 6. This here goes up in there. Or over, that is B multiplied by 2B, that is Q. Or that will now be equal to a b cubed, or a b to the fourth, or we can cancel that out. So that is 50,000 pounds per inch squared equal to 3,000 foot-pounds multiplied by 2 multiplied by 6 all over that is a b cubed. So b cubed now is equal to 3,000 foot-pounds by 2 by 6 all over that is 8 by 50,000. That is pounds per inch squared. Again, this is in terms of the foot. Pounds and pounds cancelled out. That is in terms of the foot. 1 foot to 12 inches. So we can have now this inch squared will go up together with this becomes an inch cube. The unit corresponds to B. So that we can cancel out 3 zeros. 3 zeros in here. So that is, we can cancel this out by 2's. So this will give us 4. That 2 cancelled out. We cancel out this 4 with this 12 in there. That will give us 3. So we have now the dimension of B. B now is equal to the cube root. That is equal to the cube root of 3 times 6 times 3. All over that is 50. All over 50. So that is B is equal to the cube root of 1.08 inch cube. B now is equal to 1.026. So we use now B. If we check this is our computed value, 1.026. Then 1.026 is within the range of 7 over 3 to 3. So we can make use of the lower value of 1, higher value of 1.125. So 1.026 subtracting 1 will give us 0.026. 0.026. Multiplying it by 100, that is 2.6. 2.6 divided by 1.026 will give us less than 4%. So we use the lower value. So if B is equal to 1 inch here, X now is equal to 2 relationship 2 multiplied by 1.026, or that will give us equal to how much? That is 1250. 2.0 2.052. So we use X now equal to this is 2.052. Still within the range of what 7/8 to 3. So that is our lower value is 2. This is the computed value. That is 2.125 for the higher value. This is 2 and 1/8. So 2.052 minus 2 will give us 0.0.52 multiplied by 100. That is 0.2. 5.2. 5.2 divided by 2.052, that is less than 4%. So we use the lower value. That is for the rectangle. For letter C, that is for the circle. Now, for the circle in here, C under compression and C under tension, this is still the same. So we make use again of the general form of the equation SF is equal to MC over I. So from SF is equal to MC over I, that is 50,000 foot-pounds. Pounds per inch squared, equal to the maximum moment, 3,000 foot-pounds. The C in here will be equal to the diameter, P per 2 of the circle, divided by the moment of inertia. That is, moment of inertia is pi d to the 4th all over 64. So that is now 32, and d make it cube. So our d cube now is equal to 32 multiplied by 3,000 foot-pounds all over, that is 50,000 pounds per inch squared. Converting foot to inches, so that is 12 inches, per foot. Foot and foot cancels out. Pounds and pounds cancels out. So that is now in terms D now cube is equal to the cube root. D cube is equal to 32 by 3,000 by 12 all over 50,000. So that 3 zeros here can be cancelled out. So that is now 32 by 3 by 12 divided by 50 equal is square root of cube root. D now is equal to the cube root of 23.04 inch cube. Or D now is equal to 2.845. So we use D now equal to. Again, that is still within the 7/8 to 3. 7/8 to 3. So that is 2.845. We check it. That is for the lower value of 2.845, we can have that is over 8, 2.75. 2.75. Higher value is 2.875. So lower value is 2.75. So 2.845 minus 2.75. That is 0.95 multiplied by 100. That will give us 9.5. 9.5 divided by 2.845 equal to 3.339. So that is still lower than 4%. So we can use the lower value at 2 3/4 inches. So that is if we have the cross section as a circle. Now, if we have the T section, for letter T, we are going to consider a T section. Now, using or having a T section, where the dimension I am going to use are the same dimension that we have or that I have illustrated in taking the moment of inertia for a T section. So we have here a T section. Having the flexural stress under compression and flexural stress under tension will not be the same because the C under compression and C under tension are not equal. So what we are going to consider now is to find for the C under compression and C under tension by establishing the centroid of a T-section which is referred to as a composite figure. So if we consider, if we take this upper rectangle here as figure number 1 and the lower rectangle here as figure number 2. The centroid of figure number 1, of course, is at the midsection. The centroid of figure number 2 also at the midsection, being same rectangle. So, to find for the centroid of the composite figure in here, we try to first project a reference axis. When we try to project reference axis, we have to examine, analyze the figure. If there is a possibility that when you project a reference axis, it will coincide to the centroid of the individual figure involved. In this case, if we project a reference Y, we will be able to coincide the centroid of its figure. So, meaning to say, we have to find for a projection that it will coincide with the centroid of its centroidal axis of the composite figure will become 0. In this case, our x bar is equal to 0 because the centroid of its figure lies along the reference Y. So therefore, if x bar is 0, our reference y-axis becomes the centroidal y-axis. So what we are going to establish now is the location of the centroidal axis along the x. Find for the centroid or to find for the centroid along the y, of course, that will be x1 is equal to 0. Therefore, y bar can be taken from A. Y bar is equal to the summation of AX. Capital letter A in there is the total area of the composite figure. The small letter A is the area of each element or figure involved. And X is the X element, Y element, Y is the Y element, meaning the distance from the reference X to the centroid of each figure. So we can have here the y element. That is, for figure number 1, from this point to that point, we have here a b plus a over 2. B plus a over 2. In terms in terms of a, in terms of a, that is now 7 over 2a. For the second figure, here, that is y sub 2 is equal to, from this point to this point is 1.5, 1.58, or that is half of b. Half of b, or 3 over 2a. So those are the elements. Y sub 1 element is equal to 7 over 2 of a. Y sub 2 is 3 over 2 of a. Our a element, a1, is equal to ab. A multiplied by b. In terms of a, that is a multiplied by 3a, or that is equal to 3a squared. A sub 2 is equal to a multiplied by b, or that is a multiplied by 3a, equal to 3a squared. The total area now, that is A, is equal to 6A squared. Substituting all values in here. A multiplied by y bar equal to A1. That is 3A squared by y1, 7 over 2a, plus 3a squared multiplied by y sub 2, 3 over 2a. Or our y bar now will be equal to, that is 3 multiplied by 7, that is 21 over 2 a cube, plus 3 by 3, that is 9 over 2a cube, all over 6a squared. So we will have here y bar is equal to 30 over 2, or 15a cube over 6a squared. A squared cancelled out by cube in there. So that is y bar now is equal to, by 3. So by 3, that is 5 over 2a. So our y bar now is equal to 5 over 2 of a. So we measure from the reference x-axis along the y of 5 over 2A. So that is this y bar. This being the y bar, we can now project this line, which we consider this as our centroidal x. So this is now our centroid, the centroid of the composite figure. So having now the location of the centroid of the composite figure, we can now take the centroidal moment of inertia. Centroidal moment of inertia of the composite figure, which can now be equal to the summation of I bar x. Summation of the I bar x of each figure in the composite figure, plus the summation of the AD element, AD squared element. So meaning to say, our centroidal moment of inertia, is equal to I bar x1 plus I bar x2. Figure number 1, figure number 2, plus A1 D1 squared plus A2 D2 squared. So substituting values, I bar x of figure number 1 is equal to bh cubed over 12 plus for b1 x1. For figure number 2, that is b2 x2 over 12 plus the area, a sub 1 is 3a squared. The d1 element multiplied by the d1 element squared of figure number 1. The d1 element of figure number 1 is the distance from the centroid of the composite figure to the centroid of figure number 1. So this will now be the D sub 1. D sub 1 will now be equal to half of A here and another half of A in here, so that D sub 1 is simply A. The same thing, if we locate, is D sub 2. That is now equal to, from here is 3 over 2. 3 over 2, in here 5 over 2. Or that will give us simply A. So substituting values, that is now A squared plus 3A squared by A squared. Or the base for figure number 1. The base for figure number 1 is 3A multiplied by the altitude of figure number 1. That is A cube over 12. Plus the base of figure number 2. The base of figure number 2 is A. The altitude is 3A. That is cube over 12. Plus 3A to the 4th, 3A to the 4th, or 6A to the 4th. So this will be equal to 3A to the 4th over 12 plus, that is 27. 27 A to the 4th over 12 plus 6A to the 4th, or that is equal to 30 over 12 A to the 4th plus 6A to the 4th. Or that is equal to 5 over 2A to the 4th plus 6A to the 4th. Or that is equal to, this is equivalent to 12 over 2. So 12 plus 5 is 17. 17 over 2A to the 4th. That is for the centroidal moment of inertia with respect to the centroidal x. So having now the centroidal moment of inertia, we can now consider this SFC and SFT. Say, fiber under compression. If we consider the fiber under compression, since the moment is positive, fiber under compression, so that is SFC equal to MCC over I. Substitute values. This is now 50,000 foot-pounds equal to 3,000 pounds per inch squared equal to 3,000 foot-pounds multiplied by C under compression. The C under compression is taken from the centroid to the upper fiber. It is because the upper fiber is the one that is undergoing compression. So we have taken that the location of the centroid is 5 over 2. 5 over 2 from so this is 5 over 2 of A. So outer fiber, this upper fiber lower fiber here. So we take this distance, which is the C under compression. So if that is the C under compression, that will be equivalent to, that is half of A in here and A in there. So that is 3/2 of A. The C under tension now, C under tension is 5/2, 5/2 of A. So substitute values, C under compression, that is 3/2 of A. All over the moment of inertia, that is 17 over A to the 4. So we can cancel out 1A in here. 1A, so that is Q. We can cancel out these two in there. So our A now, AQ, is equal to 3,000 foot-pound by 3. Or over 17 by 50,000 pounds per inch square. 1 foot equal to 12 inches. So our A cube now, or we take 3 zeros. So that is now 3 by 3 by 12 over 17 over 50. Zero point 503. Again, that is 0.503. That is within the range. That is within the range of 3/16 to 7/8. So lower value is 0.5. Subtracting 0.5 from 0.503 will give us 0.003. 0.003 divided by 0.503. That will give us more than 5%. So if it is more than 5%, we cannot use the lower value of 1/2. So we now use that is 9/16. 9/16 upon 8. For P is equal to 3A, which is equal to 3 by 9/16. So we have here A equal to 0.503 within the range of 3/16 to 7/8. Lower value is 0.5. So that is 0.503 subtracting 0.5. That will give us 0.003 divided by 0.503 multiplied by 100 will give us less than 5% or less than 4%. So we use the lower value of 1/2. Then for B, that will be equal to 3 by 503, or that is equal to 1.509. So we use for B, that is within the range of 7/8 to 3. The denominator of the fraction of an inch is over 8. 1.509, lower value is 1.5. So 1.5 subtracted from 1.509 is 0.009 divided by 1.509 multiplied by 100%. Ano yun? Less than 5%. So we can use the lower value, 1 and 1/2. Now having A at 0.503, we can now have our B equal to 3A, which is equal to 3 multiplied by 0.3 equal to 1.509 inches, which is within the range of 7/8 to 3. Lower value is 1.5. So 1.509 minus 1.5 will give us 0.009. Or we multiply it by 100, that is 0.9. A decimal figure divided by a whole number or larger than the numerator will give us lower than 5%. So we can use the lower value, 1 and 1/2. So these two, A and B, are the dimension based on the fiber under compression. Now, we consider that is fiber under tension. So considering fiber under tension, that is now SFP equal to MCT over I. our C under tension. C under tension is 5 over 2A. So we substitute values. That is now 50,000 pounds per inch squared, equal to the maximum moment of 3,000 foot-pounds multiplied by C under tension. That is 5 over 2 of A, or over the moment of inertia. Moment of inertia is 17 over 2A to the 4. So A in here can be cancelled out, making this at a cube unit. So this is 1 foot, 12 inches. Foot and foot cancelled out, remaining unit that is in inches. So we have here that is A cube is, or this is cancelled out. So that is now equal to 3,000 pounds, remaining unit, by 5 by 12 inches, all over 17 by 5,000 pounds per inch squared. Pounds and pounds cancels out. So A now is equal to the cube root of 3,000 by 5 by 12 all over 17 by 50,000 inch cube. So that is now equal to 5,625. 5,625. Lower value. Higher value. So higher value is 5A. Lower value is 9 over 16. We check the 2. That is 0.596 minus 0.5625 multiplied by 100. So that is 3.35 divided by 0.596. That is more than 5%. So if it is more than 5%, we use the higher value, that is 5A upon inch. So B now B is equal to 3A, or 3 multiplied by 0.596, or that will give us 1.788. So we use X. That is within the range of 7 over 8 to 3. So we use over 8. Lower value is 1.788. So lower value is 1 3/4. 1 3/4. So that is 1.75. 1. Now, look at the look at the equation. Look at the equation. What we are simply going to consider is substitute values. Substitute values, say the value taken from the fiber under compression. So if we are going to use the dimension taken from the fiber under compression substituted to the fiber under tension. So the C under tension will be smaller here. Or I mean the value of A. The value of A. So that is 50,000 pounds per inch squared is equal to 3,000 foot-pounds by 5/2A by anyway, by 12. Wait. What we are going to do is substitute the value taken from the fiber under compression to the fiber under tension. Check on the stress. Checkin natin sa stress. So, we are not going to make use of this. What we are going to consider is SFT. SFT now, substituting values. So, MCP over I. So, we substitute values. Maximum moment is 3,000 foot-pounds. Our C under tension is 5/2A. All over moment of inertia, 17/2 of A. We are going to make use of this A. So that is 0.503 inches of an inch. So we take 1 foot equal to 12 inches. So foot and foot cancelled out. So the remaining unit we will have here (17/2 A to the 4th. Tama? To the 4th. This is to the 4th. So there is an A in there. So 3,000 pounds by 5/2 by 0.503. That is inches by 12 inches. All over 17/2 by 0.503 inch to the 4th. Moment of inertia is to the 4th. Yes. So we take now the flexural stress in terms of tension. In terms of tension, which must be equal to 50,000. If we will not be able to take a value of 50,000, there is a failure on that dimension we use, which is 0.503. So what is the value of this? 83,199. That is pounds per inch square. A unit of stress. Now, if we are going to make use of the 0.503 dimension, 0.503 inches dimension on A, the stress we will be able to have is 83,199, which is higher than the allowable stress. So meaning, if we make use of this stress, 83,199, it will over-stress this 50,000. Meaning, we cannot use 0.503 for the A dimension or the dimension of A. What we can use is 0.596. Using 0.596, this will be safe because it was taken in here. The value of 0.596 is taken here. So this statement here is safe. If we substitute this value, 0.596 here on A, the stress that we will be able to have is less than 50,000 pounds per inch square. Less than 50,000 pounds per inch square, which is a safe stress. Yeah, a safe stress. So we were able to take the value for A and B under tension, fiber under tension, and fiber under compression. Now, the corresponding value of A for fiber under tension is 0.596 for A, 1.788 for B, while for fiber under compression is 0.503 of an inch. For letter B, 1.509 inches. Now, we have two sets of values for A and B. So the next thing that you are going to have is to decide which of the two dimensions are you going to use. So we decide, are these the two set of values or this value under compression? Now you can check that from the, you can use the lower value, your lower dimension that you have used or computed. In this case, we were able to compute 0.503 of an inch. So if we substitute it from this equation, SFT equal to LCT over I, meaning to say, we are going to use this dimension on the fiber under tension. So we will check it on the flexural stress or on the allowable stress. So this will be the one that will be unknown. So finding for the value of the stress developed using 0.503 of an inch as our dimension, we can see here on the computation that our flexural stress that we were able to compute substituting 0.503 is 83,199 pounds per inch squared. As stated on the problem, it was stated that we are allowed to use a allowable or safe stress of 50,000 pounds per inch squared. We developed an 83,199 pounds per inch squared. So it will overstress the allowable of 50,000 pounds per inch squared. Therefore, we cannot use that sets of dimension. Instead, we make use of the dimension taken on the fiber under tension, which is now 0.596 of an inch and 1.788 inches for B.